SwayamPrabha. Digital India. Educated India.
I welcome all of you to this lecture. Let us recall what we learned in the last lecture. We basically looked at how to have interplanetary flight. In that we learned that there is a minimum energy path devised by Hohmann, a German scientist, and through which one will take the space flight, so that it will be very efficient, and that path is known as Hohmann path. However, if you take this Hohmann path for interplanetary flight, or even to put a satellite on certain orbit, then one has to wait for certain time. That means, or in other words, it takes a lot of time to have that mission. Hence, people have devised other kinds of path, and by spending large amount of energy, and that is of course known as the first flight path. And we have also seen how one can use various burn to achieve certain flight paths, and in a gradual manner. Generally in India we use that kind of techniques of slowly and steadily reaching the requisite path, even for your moon mission or Mars mission, even placing a satellite on the geosynchronous or geostationary orbit. Later on we looked at basically limitation of the single stage rocket engines by taking an example, and we have seen that even with high mass ratio, if one cannot really place a satellite in the low earth orbit of altitude of 185 kilometer from the earth, which is the stable satellite, that is can have minimum altitude, using the best chemical rocket engine with a specific impulse of 400, and that is the cryogenic liquid oxygen, liquid hydrogen engine. Now, question arises, how we can have interplanetary flight and also place the satellite in geostationary orbit using chemical rocket engine? That questions we need to address in a today's lectures. So, let us look at what Hermann Oberth, a rocket expert, has given the idea. He says that if there is a small rocket on the top of big one, and if the big one is jettisoned and small one is ignited, their speeds are added. So, this is a beautiful concept, and what we call is basically multi-staging. And therefore, today we will be discussing about multi-staging rocket, and various kinds of multi-staging rockets have been devised. We will be discussing some of them. So, in multi-stage rocket, instead of using a single large rocket, a series of rocket engines with its own structure, propellant tank, engine is being used. And once the propellant is being consumed in a particular stage, then the rocket vehicle of the first stage, which includes the structure and also propellant tank, are being discarded or dropped, so that you can gain certain velocity for the next stage. So, let us consider a schematic of a 3-stage rocket engine, and if you look at it is having a booster rocket engine, having a nozzle, and this is your second stage, and which is having nozzle is embedded into this. So, if you look at this is your nozzles, and this is your third stage, and this payload which will be carrying this all this vehicle, rocket vehicle having 3 stages. So, once this first stage is being utilized, then this first stage, this portion will be discarded or dropped, and then the second stage will be fired, so that it will be carrying the main payload. And by using a multi-stage rocket system, we can achieve higher velocity increment as the certain fraction of the vehicle mass, as I told just now, is dropped off after the end of each stage. For example, in this case, after the first stage, this portion of the structure is being dropped off. And question arises, why it will be have attaining a higher velocity? Because of fact that the propellant in the second stage in this example is not wasted carrying the dead weight, and it is also a part of our life, because if you want to achieve a very effective and productive life for achieving excellence in life, then one has to forget about the past and remove and also the give up the dead weight carrying with us due to very bad experiences and other things, so that you can make your mind flowery, and for that you can learn from this multi-staging is very important for the life. That is why in Indian system, like the life is divided into 4 parts. First is the childhood, and then next is grahastha or the family life, and then you will have banaprastha, and then you will have sannyas. So, each stages you will be basically dropping your dead weights, and so that you will take a better flight of life. So, that is an important lesson one can learn from these multi-stage rockets, and in each subsequent stage the mass ratio will be increasing at the end of each stage. So, that you will be gaining the velocity of the vehicle, because we know that delta V is equal to V equal ln mr. So, of course, without considering the drag and also the gravitational effect. So, therefore, we will be gaining velocity by increasing the mass ratio. Final velocity of an nth stage of a space vehicle is sum of the velocity gains from each stage. That is, method can be written mathematically as delta V t is the total velocity increment is equal to delta V 1 and delta V 2, delta V 1 plus delta V 2 plus delta V 3 goes on till delta V n, and that is basically summation of delta V I, where I is equal to 1 to n, n is the number of stages. And this is corresponding to the first stage, and this is corresponding to the second stage, and this is corresponding to the third stage. Question arises, how many stages we can have? One might be tempted to go on increasing the number of stages for a particular mission, particularly for interplanetary missions, where you need to have a higher velocity, as we had seen earlier. That we will see in this lecture, that what is the optimum stages one can have. But before that, let us analyze this rocket engine stages, and we call it the tandem or the rocket in series. So, as I told that this is basically the 3-stage rocket engine example what we are considering. If you consider this, this is basically the second stage and this is your first stage, and second stage will be having some nozzle. And if you consider this mass is basically total mass of the second stage. This is basically total mass of second stage. And the total mass for the first stage, if you look at, this is m01, and this total mass of the second stage will be acting like a payload for the first stage. This will be payload of the first stage L1. This is your payload first stage. And as I told earlier, this total mass from starting from here, this is your m01. And this when you include this, basically for the first stage, this will be of structural mass, propellant mass of the first stage. And if you consider the third stage, will be having a vehicle here, and this is your basically the structural mass 3 and propellant mass 3, and this is your payload, right, payload mass. And this total is if you look at the mass here m03, that is the total mass for the third stage. And what is being done is that, as I told earlier, that second stage is started once this first stage is dropped out, and then after that this third stage will be again will be started once this second stage structural mass and propellant tank is being dropped out. Keep in mind that this M03 is nothing but your ML2, that is this portion of mass is basically payload of the payload for the second stage. And as I told that if you can take for ith stage, this will be m0 r is the total initial mass of the ith stage prior to firing, including the payload mass, and MPI is basically mass of the propellant in the ith stage, and MSI is the structural mass of ith stage alone, including the mass of the engine, controller, instrumentation and residual propellant at the burnout, because at the end of burnout there will be certain amount of propellant will be remain unused. So, that mass also will be taken as a structural mass, and which will be dropped out at the end of each stage. So, if you look at, we need to really find out basically delta V n. If I take this delta V n is of the change in velocity or the velocity increment of the ns stage is equal to summation of delta V I when I is equal to 1 to n. N is the number of stages. So, that we know if we will take only space component of this velocity increment for the simplicity, and we will find out this is V E 1 ln m r 1 plus V E 2 ln m r 2. It goes on till V E n ln m r n. So, therefore, we can look at it and then the summation, and if we can assume V E 1 is equal to V E 2 is equal to V E n, then we can write down this, let us say equation 1 becomes delta V n is equal to I can write down as V E ln m r 1 dot m r 2 m r n. And we know that this m r, because as m r is equal to basically V naught minus burnt out mass. So, therefore, I can write down this V E L N m naught 1 by m b 1 into m naught 2 by 2, it goes on like that, m naught n divided by m b n. And we know that burnt out mass is nothing but your m naught 2, right. So, we can write down that as, and because this will be coming out. So, we will assume that this will cancel it out, you can do that, and that is equal to delta V n is equal to V A ln m naught 1 divided by m b 1 b n, and that is equal to, you can write down V E ln m naught 1 divided by m 0 n minus 1. So, what you can see that it is also, you can write down that as it is, if I take assume that m r 1 is equal to m r 2 is equal to m r I. So, I can write down this delta V n is equal to V E n L n m r I, and I can be basically 1 to n I power to the n, because all are these things. So, that it will be going on. So, this is I can write down as n V equivalent ln m r I. Keep in mind that we can write down that we know that m r is equal to basically m naught divided by payload mass plus structural mass 1 by m L by m naught plus m s by m naught, and this we know that is basically payload fraction, and this is your structural fraction. So, I can write down as L f plus S f. So, similarly, we can write down this here as delta V n is equal to n V E ln 1 minus LF I plus SF I. So, we will see now how this LF I, the payload fraction, will be dependent on the number of stages, and generally the structural fraction will be remaining constant for all stages, that is as a part of the design. So, if you look at LF n, we know it is basically payload mass of nth divided by m initial mass and is equal to m l m l n divided by m naught O n into m naught O n. This is the basically payload, that is m naught O n minus 1 into, this goes on, m naught 2 divided by the m naught 1. So, we know that this is basically LF n and this is LF n minus 1 and this is your LF 1. So, that itself we can write down as LF I power to the n, because if I consider this as same for all, right, the payload fraction is same, LF n is equal to LF n minus 1 is equal to LF 1 is equal to LF I. So, therefore, I can write down that as basically LF I is equal to LF n power to 1 by n. This is your equation 2. So, if I can club this equation, earlier equation, that is basically delta V is equal to n V E ln 1 by L F I plus S F I. I can write down as n V E ln 1 by L F n power to the 1 by n plus S F I. So, by that I can also write down this is delta V by V E is equal to n ln 1 divided by L F n 1 by n plus S F I. So, this is your expression which you can tell me which depicts that change in velocity for n number of stages, and of course, this LF n is a constant for the entire range and SFI is also remaining constant for each stages. So, if I will plot this delta V by V for number of stages, we can get variation of velocity increment with number of stages. We can see that delta V by V equivalent to it is goes on with the number of stages, and this is being plotted for SFI of 0.5, LFN for 0.15. You can see for the number of stages, if it is 1, there will be some velocity increment, but if you go for the number of stages, the velocity increment is reduced further, and if you go for number of stages, there is not much gain in velocity change, and if you go for 4, there is hardly any changes in the number of stages. Therefore, it is advisable to go for the number 3 stages only, because you are not gaining anything going beyond the 3 stages, and keep in mind that this is being used, right, because there is no change in the velocity or In other words, in comparison to the complexities involved in more number of stages, we are not gaining anything going for third stage or 3 stages, we are going for beyond the 3 stages. So, therefore, generally the 3 stages of rocket engines is being preferred. Just now we have discussed about the variation of velocity increment number of staging. Now, we will look at the various kinds of staging as being devised by various scientists, and there are several of them, but we will be discussing 3 of them. And let us look at the stages in series, tandem stagings. So, this is, as I told earlier, that this is having 3 stages rocket engines, and which is having the first stage and having 3 stages. And keep in mind that once this first stage is being utilized, or in other words, if it is when all the propellant of the first engine is consumed, then this will be the structural mass of the first stage will be discarded, and then the second stage will be ignited such that it can take the flight further. And in the similar fashion, the third stage also ignited after the second stage being separated out. Keep in mind that this is a very important one and which is being used very much, but however, it is not being used nowadays alone, and there is some of the problems what is being faced in the stages in series is that how this first stage will be separated from the second stage. Unless it is ejected properly and in the right time, then it may miss the required flight path. If there is a delay between both the separation and ignition of the next stage, then there will be a problem. Of course, this problem being solved, and then now people are very accurate in doing that, and keep in mind that this is not being used alone. Nowadays, people are using the parallel. If you look at this is the again the tandem stagings, and along with there is a maybe 2 or the 4 or the kind of strap-on motors. This is strap on motors is being used, and which will be parallelly being ignited. And once this is all the propellant is adjusted in a strap-on motor, then it will be ejected out, that means it will be moving out, and then the first stage will be running, and once the first stage being adjusted out, and that will be dropped, and the second stage can be initiated, and it goes on. So, this is being used very much in our GSLV and other also vehicles, because in the booster rocket, in the booster phase, we need to provide the very high thrust level. Therefore, this parallel staging is very much essential, so that it can be more compact, and after of course, the first stages of the booster phase, then you do not need to have a higher thrust, you can manage the second stage and third stage. And there is another thing which is being used is the piggyback, which is being shown. This is your booster phase rocket and the sustainer, and it is like an aircraft where a crew member can be really returned back from the flight, and this is being used very much for the as a reusable vehicles. But however, the drag component of this piggyback is much higher as compared to the parallel or the tandem stagings. But this is very essential for the manned mission. As I told, it has been already used by the USA and other developed countries for making their manned mission success. And let us look at a GSLV flight profile, GSLV D5. If you look at, it is having a vehicle here, and this is your core stage strap-on ignition, and strap-on ignition core stage ignition will be starting at around something 0 seconds, and then strap-on ignition will be before that it will be started on minus 4.8 seconds, and the strap-on sort of, that means this will be separated out strap up, as I told it will be something 2 minutes 29 second and at the an altitude of 70 kilometers, by which it can reach the velocity of 2399.9 is basically 2400 meter per second. And then after this vehicle, if you look at, this is your first stage separations which will be occurring, that will be occurring 2 minutes 31 second kind of thing, and second stage and ignition will start basically little before that 2 minutes 29.5 seconds and at an altitude of something 70.98 kilometers, and which will be gaining the 2401. There is a little bit gain, but however, after this is being there, then it will be gaining more, and the payload fairing, that means it will be separated out, right, which will be taking place around 3 minutes 46 seconds at an altitude of 115 kilometer, and it will be gaining the velocity something 3393 meter per second. Then GSLV GS2 setup will be there. This is your second stage and then of course, setup will be there. Second stage separation or the cryogenic upper stages is being used around 4 minutes 52 seconds, and it will be now the velocity will be 4945 meter per second. And cryogenic upper stage, this is burned out period, and which will be occurring, and something 9785 meter per second, and of course, like one has to ignite, it is much earlier, like a little bit after the second stage separation, the cryogenic upper stage ignition takes place. And when this GSAT will be separated out, it will be gaining something 9778 meter per second, which is much higher. So, if you look at the when the strap and setup was there, it was only 2400 meter per second, but it has gained to something 9778 meter. So, it is a lot of gain being achieved in velocity increment by using the stages. So, you can see that what the operation is being there. Thank you very much. We will be basically discussing about in the next lecture chemical propellant. Thank you very much.